the menu here. So what I would like to do is I would like to give you a little bit more information about the self-consistency condition, which at this stage has been written into this form, which is a little bit mysterious, so I would like to make it a little bit more explicit. And in many of the talks, you've actually been hearing people alluding to the Bethe lattice, okay? So I want to explain what this is and make it simpler in this case. Okay. Then that will allow you to understand better what we mean by the fact that the Weiss dynamical mean field is related to the local Green's function by a self-consistency condition. You will see that in this case, this condition takes an extremely simple form. Okay. Then I would like to go back to the basic physics of the Anderson impurity model. I would like to explain how this physics depends on the low energy behavior of the bath or of the hybridization function delta of omega. Okay? And that will take you naturally to understanding how in the DMFT self-consistent equations we can have something like a metallic phase and a Monte insulating phase, and where these solutions exist in the phase diagram. And this is basically my agenda. Is there anything else that you guys would like to know? And that I could reasonably cover in, I don't know, 40 minutes or 45 minutes? Okay, good. Okay, so let me first explain a bit about this. So here you see that we have the self-consistency condition as written for any lattice you want. Okay, you just give me the tight binding band epsilon k, okay, which comes from your hopping on a specific lattice, and that would be what DMFT tells you to implement a self-consistency condition. However, you see this is a bit of a, even though this relation is diagonal in frequency, and it doesn't couple the different frequencies, it's a bit of a nonlinear equation. If you give me a G, I cannot give you immediately a delta. I have to solve this equation one way or the other. So let me make it a little bit simpler. So for this, we can consider the case of the so-called Bethe lattice. And who knows what a Bethe lattice is? Oh, not too many people. Okay. So on a Bethe lattice is actually a tree. So it's also called Cayley tree, I think. So it's a tree like this. Okay. So you see it's a little bit of a strange lattice because it's certainly not a Bravais lattice, and you know, you don't really have a well-defined Fourier transform on this. Okay. This is an example of a Bethe lattice in which each site has connectivity Z equal 3 in the case of my drawing. You see that the connectivity of this lattice, the number of neighbors of any given site is 3. Okay? In fact, we can consider the limit in which the connectivity of this lattice goes to infinity. And in this case, sorry? Is it always what? You're talking about boundary conditions? Boundary conditions on the Bethe lattice is a subtle issue that I don't really want to deal with, okay? But that's a good question. Let me skip this under the rug. Okay. So what I claim is that in this limit, the DMFT equations solve the physics of solve the Hubbard model on this lattice in the limit of z connectivity goes to infinity, and that in this case, the self-consistency condition takes an extremely simple form, which is delta of I omega equal some parameter that I'm going to call T star square times G over I omega. So you can't think of a simpler form of this self-consistency condition because it basically just tells you that the hybridization function should be just proportional to the local Green's function. So for all practical purposes, essentially the same object. Yes, so that I'm going to explain now. Okay? So we need to define properly that limit, z goes to infinity. Okay? And as in any stat-mech model, when you do that, you have to ensure that the potential energy and the kinetic energy actually scale in the same manner as z goes to infinity. Otherwise, we lose the physics of all phase transitions and so on, and competition between kinetic and potential energy, which is at the heart of this problem, delocalization and mode localization. Okay, so you can show, I'm not going to do it in detail on the board, but it's not too difficult. You can actually show that the proper way to do that, if you define a tight binding model on this lattice, with nearest neighbor hopping on each of these bonds, Tij, so this is Ij, nearest neighbor hopping, Tij, electrons hopping around. The way to do that is actually to scale Tij as T star over square root of the connectivity. Okay. So for those of you who want a quick justification of this, even at that time of the day, I may be able to try. Okay, so let's consider the free electron problem on this lattice. Okay, so the free electron problem on this lattice will have an effective action which will be something like d tau, okay, plus mu or minus mu or whatever, times delta ij, okay, minus Tij d dagger I dj sigma. Okay? And I can try doing something which is called the cavity construction, in which I am going to integrate, I'm going to consider a given lattice site here, let's call it 0, and I'm going to integrate out all the other sites in the lattice, except that given site. In the case where u is 0, it's actually very simple to do that because this action is completely quadratic. Okay, so I can easily do that. Okay, so what am I going to get? You see that here, the only, so maybe I need to erase a little bit. You see that in this case, my effective action for that specific site 0, which is at the center, okay, is equal to a local part, which is just the one here. Okay? There is an integral d tau, of course, and so on. Okay? And then all the other terms, there is no u here, I'm just doing tight binding, okay? All the other terms couple this site to the neighbors, right? So here I have a sum, okay, for all the, say, j neighbor of 0 of T j0 d dagger j sigma times d0 sigma plus the other term in which I would interchange the dagger and the non-dagger. So you see this is a term that is linear in d0 sigma. This is a term which is quadratic in d0 sigma. And then, of course, I have, so the full action of the problem will involve other terms that are quadratic in the other variables the ones that live everywhere else, okay? And it will involve the hopping and so on, okay? So I would call it S rest, okay? Rest of the lattice. So this is the local action of site 0. This is an action that couples the central site and the neighbors, and this is something that lives everywhere else. Okay? So now let me actually integrate out all the dj sigma. So it's very easy to do because this action is quadratic in this case. Okay? And I just have two quadratic actions and a linear term that couples 0 with the other neighbors. And so I can integrate out, let's imagine you can do Gaussian integrals just like that, okay? Even at that time of the day, I more or less can do it too. And so what you get then is that the effective action for that site 0 is equal to this, which of course we didn't do anything about. And then this term will lead me to the following thing. Let's see if I can do it, okay? So I have to do, so this is like a source term, eta, for site 0 at time tau, okay? So what am I going to get here? I'm going to get integral d tau prime, source term at time tau, source term at time tau prime, times a kernel, which is the Green's function of d dagger j sigma d j prime sigma. So I'm going to get something like this. Sorry, the source term, that's not exactly right. The source term I should think of is a source terms that couples to dj sigma, and which is really tj0 d0 sigma. This is what I really mean, okay? So here I'm going to get, let me do it properly, something like sum over jj prime d tj0 tj prime 0 d0 sigma at time tau, d0 dagger sigma at time tau prime, and here are some Green's function which connects sites j and j prime, and which depends on tau minus tau prime. But this Green's function has to be calculated in the theory in which this bond and this site have been removed, okay? Because I have, it knows only about this action S rest. So let me put here cav, which means that I have digged in my lattice a little cavity. Okay, so now let's look at this, you know. First of all, everything here is non-interacting. So this G is really also the non-interacting Green's function of the problem. Second, if I have removed here a little cavity, obviously J and J prime cannot communicate except if they are in the same sublattice. That's a particularity of the Bethe lattice. And since they have to belong to the first shell of neighbors of 0, the only thing that can be is that J is equal to J prime. Okay, so then this sum is really over J. Here we get Tj0 square. And here we really just have, let me rewrite this, d dagger 0 sigma tau, d0 sigma tau prime, g jj with the cavity of tau minus tau prime. Good. So now comes the catch. You see that this tells us that So now let's take the limit. Z connectivity goes to infinity. In that limit, it really does not matter that we have removed one side from the problem. So this GJJ cavity should be absolutely identical to the one without a cavity, because it's a 1 over Z perturbation effect. So here I can remove cavity, and if my system is completely translationally invariant, all these GJJs are all also equal, right? And so I'm left with the following equation. You can read off directly the local Green's function of this problem, which is the inverse of this kernel, and you have derived for u equals 0, right, that g minus 1 local is equal to what's written in front of you on the board, namely I omega n plus mu minus something which is sum over j of tj0 square, right, times g. That's what I have derived. Okay, so now, all the hoppings are the same on all bonds, right? So this is just the square of the hopping times the connectivity of the lattice. Zc times t square. So you see that if we have to make sense of the large Z limit, Zc times t square has to be a fixed number, right? Which I called t star square, okay? And so we have to scale the individual hopping on each bond like t star over square root of Zc. The same kind of mathematics can be done, if you don't like Bethe lattices, directly on the cubic lattice, taking the limit of large dimensions. The same sort of scaling happens. That was the observation of Metzen and Volhart in the original paper. But in this case, the cavity construction is a bit more complicated because different sublattices can actually still communicate, even in the presence of the cavity, and the final equation is a little bit different. But the philosophy is the same. Okay, so let's look at this equation. Here you see this equation becomes t star square g. Anybody can solve this equation. This is a quadratic equation, right? And so what you will find is that the corresponding density of states, d of epsilon, okay, which is, or d of epsilon, let's say, let me call epsilon omega plus mu, okay, d of epsilon of this Green's function, which is minus 1 over pi imaginary part of g, okay, is actually a semicircular law, okay, of width, if I remember correctly, 2t star, okay, and it's correctly normalized and so on. So it is something which is square root of 4t star square minus epsilon square with an appropriate normalization, which is probably actually 2 over pi t star, if I remember correctly. I'm not sure. Okay, doesn't matter. Kind of. Okay, so doesn't matter. Good. Okay. So actually, you see, so let's now consider the case where u is non-zero. So let's do u different from 0. And what I'm going to show you is that very, very little is changed in this mathematics of the cavity construction. So for those of you who want to learn the details of this cavity construction, you can look at my review of modern physics, oldish review, okay, where this was first presented. So let's repeat all this cavity construction. Now in the interacting case, what will happen? What will happen is very little changes. We will still be able to integrate out all these other sides, except the integral is no longer Gaussian, right? Because this action S rest, okay, contains the U term. Also, the local action contains the U term. So my local action contains still d tau plus mu d dagger d and so on. It also contains the term u and up and down, okay? And then when we integrate out the whole goddamn thing, okay, we are going to get a first quadratic term, which will be exactly the same now with the true interacting Green's function, because integrating out these other terms produces the generating functions of the Green's function. So we are going to get here integral d tau prime, t star square, d dagger tau, g of tau minus tau prime, the full interacting Green's function d tau prime. So this is essentially the same as what we just did, except now we are going to have all sorts of higher order correlators. We are going to have plus integral d tau 1, d tau 4, okay? 4 source terms, and some awful two-particle correlator of our model, and so on and so forth. It's an infinite series. The beauty of that game is that you can show that because of this scaling, all these higher order terms in the limit of z goes to infinity disappear. And the only important term is this guy. Okay? So all these guys are only there as 1 over z corrections. In the limit of z goes to infinity, we have derived explicitly from this cavity construction the mapping of the local properties of the Hubbard model onto an Anderson impurity problem. Now it's a mathematical, essentially, well, I wouldn't say mathematical proof, but it's a, you can follow the algebra from line 1 to line z, okay? And you conclude that my problem is a local impurity problem with a Green's function g0 minus 1, which has to be self-consistently related to the full interacting local Green's functions by this relation. This relation tells you that delta is t star square g. Right? Okay, so question, is this equation consistent with this one? Because here we've done two completely different pieces of mathematics. So exercise for the students, take a semicircular density of states for epsilon k, do this integral, it can be done analytically. You will show that you can then invert explicitly this equation to get this one. Okay? So everything I told you is consistent. If you take a semicircular, put it there, do the integral, invert the equation, you will get this conclusion that I reached here by direct means from the cavity construction. Okay? Fine. So what I've shown you here is that if you are really interested in having a controlled mathematical limit where DMFT works, you can take lattices of various topology, but you have to take the large connectivity limit always. There is one which is particularly simple, which is the Bethe lattice, which has a semicircular bare density of states, so it's a very reasonable band, okay? And in which the self-consistency condition is very simple. The hybridization has just to be proportional to G itself. Okay? And while doing that, I've also derived for you the DMFT equations explicitly. Any question on this? Okay. So now I will switch gears and do something less formal, okay? More physical. Good. So now the question on the table is, we are instructed to solve a self-consistent impurity model in which we start from a delta, we calculate a local G, and these two guys should be related just to keep, can you see if I write here? No, okay. So we start from a delta, we calculate a local G, and these two guys have to be related by a self-consistency relation, which in general is this, but let's just keep in mind a simple case because it doesn't really change the physics. Let's assume that this is the relation. That's the problem. And one word of caution, this form of the equation is, or this one, is only valid in phases in which there is no spin or translational symmetry breaking. If I wanted to describe the red phase, the antiferromagnetic phase, I would have to modify the structure of these equations to account for spin symmetry breaking and two sublattice translational symmetry breaking. It can be done. We can write these equations, but not tonight, okay? Good. So we want to understand what will come out of this problem, of this self-consistent problem. First thing you need to understand is what comes out of a non-self-consistent problem. So again, let me give you a 5-10 minutes crash course in the physics of the Anderson impurity problem. I remind you that our Anderson impurity problem is a single level atom embedded in a host. And we've seen that depending on epsilon d, the ground state of our atom can be either doubly degenerate or empty or doubly occupied. Okay? So, obviously the interesting regimes, the regimes that are tricky, are those ones and also the mixed valence regime. And now the question is, I branch on a hybridization, which means I branch on a function delta, which allows hopping to the bath. What will happen to these guys? Okay? So, let us look at the structure of the spectral function in first the absence of hybridization and then the presence of hybridization. And since it's getting late, I'm going to do it only in the case where we are exactly at half filling epsilon d is minus u over 2, and we have particle hole symmetry. We can discuss other cases later. Okay, so in this case, the ground state is doubly degenerate. And the spectroscopy of that atom is very simple when there is no delta, okay? And it's as follows. If we compute the spectral function, by now, thanks to VJ, everybody knows what spectral function is. We can either remove an electron from that ground state, and this will give me an energy, which is the difference between this energy, which is epsilon d, and the energy of the empty state, which is 0. So this energy difference is epsilon d, which here is minus u over 2. So this will give me a peak here at minus u over 2, which corresponds to the removal spectrum. Okay? Similarly, I can add an electron. The energy difference for this is 2 epsilon d plus u minus epsilon d, which is epsilon d plus u, which in this specific case is also equal to plus u over 2. So here I would have another peak at plus u over 2, but you should really remember that this is something like epsilon d, and this is something like epsilon d plus u more generally, which corresponds to this transition. Okay. So now what will happen when you couple in an hybridization? First thing that will happen is that each of these sharp atomic transitions will become broadened. It will become broadened by an amount which is associated with the Fermi golden rule. So V squared times the value of the density of states in the bath. So basically the hybridization function at the corresponding energy, which is there. So the thing you expect is that these things will become broadened, okay, with an energy which is with a width which is something like imaginary part of delta at the corresponding energy that I'm looking at. That's essentially what happens. And there are minus 1 over pi's, and don't bother me about prefactors right now. Okay. But the real question is what happens, so what are these guys, okay? These are the vestige of the atomic transitions dressed by the solid state environment. They still have this physical interpretation, and they go under the name of Hubbard satellites, okay? So this is the so-called lower Hubbard band. This is the so-called upper Hubbard band. has nothing to do with a band, really. Okay? It amounts to removing an electron, creating a hole, and then looking at how this hole propagates. But this hole, actually, if you look at k-resolved spectral function, you will discover that this quantity has also a very short lifetime, okay, which is of the order of that width itself. So it's not really a band. It's an incoherent excitation. But the really important question is what happens here? What happens close to the ground state, which is zero energy? This is omega, excitation energy with respect to the ground state. What happens there? So the question about this is whether this double degeneracy of the ground state is lifted or not by the presence of the hybridization. This problem you can understand very simply by considering the case where your impurity model, your atom is just one level, is coupled to, let's say, only one level in the bath. So let's consider a very simple caricature of this impurity model where instead of a full continuum delta of omega, I just have one level in the reservoir. Okay? And since I'm interested into ground state property, this guy, this level I take essentially at zero energy. Okay, so now the question is, in the absence of any hybridization here, right, the ground state of this is doubly degenerate. Now I allow electron to hop there. Okay? So you remember the super exchange story that I described before. It's almost the same problem, except there is no U here on that side. This side is free stuff. But it's almost the same thing. And since it's almost the same thing, the same story applies. Namely, out of these degenerate states that I will have by, this side can also be occupied by 1, 0, or 2 electrons, okay? And if it's occupied by 1 electron, I can also form a singlet and a triplet sector. The singlet sector will be screening this local moment by an antiferromagnetic coupling between the bath and the local orbital. And the triplet will be like this, okay? So same story. Actually, if there is a state in the bath at zero energy, let's say, the singlet state will be favored, okay? And the singlet state will be favored over the triplet one by an amount which is proportional to V square over U. This is called the Kondo coupling in this problem. It amounts to an effective antiferromagnetic interaction between the spin on the local moment and the spin of conduction electrons in the reservoir. Okay? So from this, you would guess, and this is the simplest strong coupling description of the Kondo coupling, this mapping can be done in full glory, and it's called the Schrieffer-Wolff mapping in this context. And what you learn from this is that if there is a low energy state in your bath which is able to screen your spin, then the spin will be screened into a singlet and no local moment survives. The ground state becomes non-degenerate, right? And the hybridization is a singular perturbation. Immediately it lifts the degeneracy of the ground state. So what we've learned from all this blah blah, okay, is that if there are states in the bath at low energy, which in technical terms means if the density of states of my hybridization function, which is really this, okay, is non-zero at low energy, right, then there will be Kondo screening, and you know from Thomas what this means. What it really means is this, formation of a singlet between the local atom and the reservoir, Kondo screening of local moment, non-degenerate ground state. Okay? Now, what if this is not the case. If this guy, 1 over pi im delta, is 0 at 0 energy, okay? That means there is no state here in my bath. Perhaps there is at higher energy, but not at 0 energy. So then you cannot form an antiferromagnetic Kondo singlet, and hence your hybridization to the bath is not a singular perturbation, and the ground state remains happily or unhappily degenerate. So local moment remains. There is no Kondo screening. It's like putting a magnetic impurity in a wide band gap semiconductor. No screening is possible. Okay? So no Kondo screening. Local degeneracy, ground state degeneracy remains. Okay? So in the context of a magnetic impurity in a metal, we put a manganese atom in copper. Copper has lots of states at the Fermi level, no question. So there will be Kondo screening. In the context of DMFT, we don't know, because delta is not pre-ascribed for us. It is self-consistent. So what is this telling us? What is this equation telling us? It's telling us that, let's calculate 1 over pi im delta, right? So this is telling us that minus 1 over pi im delta is T star square, which is just a number, times minus 1 over pi im g. What is this? This is the spectral function at 0 energy. So what we are trying to do is to screen the local moment with the states that are in the self-consistent solution of the lattice Green's function itself. Our bath is also our local spectral function. Imagine you have a metal, a metallic solution of these equations. By definition, it means this is finite at 0 frequency, right? Because that's the definition of a metal. That means the bath will have states at 0 frequency. This means we are in case 1. There will be Kondo screening, which means there is no local moment. Indeed, in metals at low energy, there is no local moment. So the metallic solution is a self-consistent possibility, right? Now, imagine we have an insulator, good, honest Mott insulator with a Mott gap. It means this is 0 at 0 energy. It's also 0 over a finite window of energy in the gap. It means then that the bath has no states at 0 energy. It means that, indeed, there is no Kondo screening, and that, indeed, the system has a degenerate local moment ground state, which means blah, blah, okay? But here we have other possibilities, which is impurity in a system with a gap, no Kondo effect. And we need to know, as a function of the bare parameters of the problem, which one of these two possibilities emerged. Okay? This is why we say we have to deal with a self-consistent Kondo screening problem. And the solution of that problem may be Kondo screening takes place, that's the metallic phase. Kondo screening doesn't take place, that's the insulating phase. Okay, do you have questions? Okay? Fine. So now, in the 5 minutes that remain, I will tell you what actually happens when you solve these equations. So what actually happens, well, actually I have a movie of this. So let me show you the movie, because at 5 minutes before dinner, probably movies is all you want to see. So let me try with a movie. I have always trouble launching this movie. This is my problem. Okay, so the movie. Let's see how this works. Yes. So now, what I need to do is to get my mouse to go there and click on start. So this is a semicircular density of states. Okay? U equals 0. And what we are going to do now is we are going to solve this self-consistent problem increasing U. So each of the images you're going to see is a converged solution, and we just increase U gradually. And the solver that is being used here is precisely this iterated perturbation theory solver that you learn how to program thanks to the great codes of tricks tomorrow yourself. Okay, so you'll be able to realize this movie tomorrow yourself. But here I'm showing you the result. Okay, so let's see if this works. I, of course, lost the launcher. I still need to get my mouse to be there. Just be patient, I'm coming there. See, I need to have coordination. And then click. And it doesn't work? Why not? Shit. This should work. Just a second. I'm going to get it to work for you. Is anything happening here? No. Oh, well. It's doing it? Okay, so see what happens. Watch the movie. So the band narrows. I'm doing the commentary, okay? Spectral weight is transferred to these atomic excitations. We form lower and upper Hubbard band, and a quasi-particle band here. Quasi-particles become massive, narrow bandwidth, some bizarre things happen, and at some point, see what has happened? What is this? A Mott insulator, good. Okay, and now we have a Mott insulator with wider and wider gap. Don't pay attention to all the wiggles, okay, just well, I mean, some of these things are real. I don't want to enter into any of these. But basically, that's what's going on. Okay, so what this movie shows you is that as a function of coupling, we are taken from one kind of solution of this self-consistent problem to another. If you actually, just to finish, if you actually do this carefully, what you will find is that the situation is actually a little bit more tricky, and that let me do 0 temperature as a function of U over T star. What happens is, so beware of what I'm doing here. I'm describing the solution of the paramagnetic DMFT equations at 0 completely well-defined mathematical problem. I have to solve this problem at 0 temperature. But I'm not telling you this is the ground state of the Hubbard model, right? The Hubbard model at 0 temperature will have an antiferromagnetic ground state, which has a lower energy than the solution of these paramagnetic equations, right? But I'm still looking at the solution. I can do that because this solution is well-defined. This is a beauty of mean field theory, that you can always continue solutions, even if they have not the lowest free energy. Okay, so what happens to this solution? In fact, there is a metallic solution up to some coupling UC2, and there is an insulating solution that you see here down to some coupling UC1. So everywhere here, the DMFT equations converge to a unique solution independently of the seed delta. All the way here, there is also a unique solution, is insulating. Here in this region, there are 2 solutions, which depends on your initial seed. If you start from metallic delta, you go to the metallic solution. From an insulating delta, you get to the insulating solution. I didn't tell you they have the same energies, and they don't. The metallic solution is always the lowest energy solution. This extends to finite temperature, where, in fact, there are 2 spinodal lines like this, which merge into a second-order critical point. And there is somewhere here a first-order transition between the 2 solutions, a bit like a liquid-gas system. Okay, it's too late to discuss the details, but it's something like this, okay? Now, to do a complete job, we also have to draw the antiferromagnetic phase boundary. But the point is that this phenomenon, which happens at very low temperature, everywhere here it's a crossover. Okay? This phenomenon is really the root, the seed of the crossover. So here there is a, a Mott crossover, and there is a crossover which has to do with the quasi-particle scale. You remember these two crossovers. To understand this crossover, you actually have to be able to track them to this physics. So the beauty of this theory is that actually it allows you to route the crossovers into something which is a lot less ill-defined than a crossover, but actually see that they emerge from some underlying critical behavior of the paramagnetic solution of the problem, notwithstanding the fact that in real life, all these phase transitions may well be hidden by the antiferromagnetism. This depends a lot on the lattice. The situation may be like this on an unfrustrated lattice. Situation on a frustrated lattice may be like this, hence revealing this critical behavior, But the crossovers you wanted to understand in the paramagnetic phase are really rooted in the phase transitions that happen in these equations in the limit of 0 t. Okay, that's it. Questions?
During the dinner, I guess.
Well, we can have some questions now. Maybe the students first. Otherwise, they won't say anything. This business. Okay. So I've devoted all our efforts up to now describing for you the DMFT equations in the paramagnetic phase, right? But I taught you this morning the Hubbard model also has an antiferromagnetic phase. So we have to repeat the same job. We have to write, and DMFT also has an antiferromagnetic phase, of course. Actually, it even overestimates TNL, right? Because it's mean field. So we have to repeat the same business in the antiferromagnetic phase, stabilize all these solutions, compare their energies, and draw the final phase diagram. Okay. Whether the system, the value of TNL, which is this guy, okay, depends a lot on the nature of the lattice you are on. And there are basically two possibilities. Let me be clear, perhaps more clear than I was. One possibility is that antiferromagnetism is happily unfrustrated. That will happen on a cubic lattice, for example. And that Néel phase is something like that, while the phase transitions of the paramagnetic solution of DMFT is something here. This is more or less what happens on the cubic lattice. So there is a whole story you can discuss, okay? But this is really hidden in real life by antiferromagnetism, and the only thing you will see are the crossovers corresponding to the formation of the gap and corresponding to the vanishing of the quasi-particle, which is the narrowing of this bandwidth. And what you have at the end of the day is something in which you should basically erase this, say this is antiferromagnetic insulator, and forget the yellow lines there, right? And here you have crossovers that you can understand because you've routed them to the yellow lines, okay? Between metal with coherent quasi-particles, some bad metal, some paramagnetic multi-insulator, right? So you could say this is science fiction because it's hidden by antiferromagnetism, but it's not, because we had an agenda of understanding this, right? And these crossovers will be slightly modified by magnetic correlations, but only slightly at high temperature, right? So that's what we've done. Now, another possibility is that the magnetism is so frustrated that what really happens is that the antiferromagnetic phase is much smaller, and these guys do emerge out into a real phase transition. And this does happen also in nature. Both situations happen in nature. V2O3, for example, or the kappa ab-initio organics are like this. Why? In the kappa ab-initio organics, we have a triangular lattice structure, very bad for antiferromagnetism, okay? And in these systems, like oxides, we have competing orbital fluctuations that deplete the magnetism. We also have coupling to the lattice that help promote these crossovers into phase transitions at which actually the lattice reacts. I studied this with Krish many years ago, this feedback of lattice, and, okay? But both solutions are possible. So V2O3 has a diagram exactly like this, antiferromagnetic insulator and a first order phase transition between a paramagnetic metal and a paramagnetic insulator. Other questions? Same guy.
Same guy.
Okay.
Yeah. So the kind of order you are looking for, that is you encoded in the initial guess for delta omega you are giving.
No. The order, you mean the real magnetic ordering?
Yeah.
You are talking about magnetic ordering, or
Yeah.
what?
Yeah.
I haven't talked about magnetic ordering at all.
No, I'm saying whether you are
Metallic or insulator?
Yeah.
Yes. Well, these equations have well-converged, unique fixed point. There can be only one or two, but not 10, okay? So when there are two, which is this region, this tiny region here, okay? There is one fixed point whose attraction basin is all initial deltas that are metallic, basically. And there is another one, which are all the attraction, all the initial deltas that are insulating. There is also an unstable solution. I don't want to discuss this, okay? You understand what I'm saying?
Yeah, but how do you know which delta is which? I mean, which initial delta leads to?
No. I have to converge this loop and find the fixed points. I find them. There are only two. I don't care about the initial delta. This is something for running your computer. It doesn't matter, okay? I identify the two converged solutions. And then I have to compare their free energies, which you need to be able to calculate and decide which one is the physical one. Delta, initial delta, is just an initial condition. Okay?
So that small triangular thing between
Yes.
UC1 and UC2,
Yes.
that can be interpreted as coexistence of the metallic and the model study.
Yes, it's like exactly like the spinodal region. You know, in a liquid-gas transition, there is a spinodal for the liquid and a spinodal for the gas. It's the same thing. It's the regime of stability of the different phases.
And how do you extract that small line that you put in the middle of UC1 and
You calculate the free energy and decide which one has the lowest solution. So if you plot, for example, double occupancy as a function of U through this region here, what you will see is that there is a solution which is the metallic branch, which has high double occupancy, a solution of the insulating branch, which has very small double occupancy, right? And so this is UC1, this is UC2. Somewhere there is the first order transition, so that guy jumps. As you raise temperature, this thing becomes gradually smaller and smaller, and at some point it becomes like this with a vertical tangent, and this is this TC. Okay? But you need to do quite a bit of work. You need to stabilize these two solutions, calculate their free energy, find the first order line, if you really want to do that.
So how did you get that antiferromagnetic curve there? Because from
right now I have not described it.
Okay.
Okay? What I need to do is I need to allow for spin symmetry breaking. So now this guy will obviously be dependent on spin, so that generalizes the equation. And I also need to generalize that guy. On the Bethe lattice, very simple.
Okay.
I can write it immediately. Because an up electron on sublattice A will hop to an up electron on sublattice B. But an up electron on sublattice B is like a down electron on sublattice A. So the equations are that. These are the equations in the antiferromagnetic phase on the Bethe lattice. Now you have to run this. It's a different set of equations, and you'll find the antiferromagnetic solution.
So then here also we will get two solutions. One would be the antiferromagnetic and the magnetic.
No, I believe, well, okay, I'm not completely clear about that.
If you allow the symmetry effect, it will go into the antimagnetic. But you can ignore it. In that case, you have ferromagnetic, but the antimagnetic is the one that's stable.
Yeah, yeah. But I think your question is, in the antiferromagnetic phase, do I have only one kind of solution? And I think the answer is yes. Of course, there is a gradual change in the nature of this solution from Slater to Mott within this red phase. That's another story.
Thank you.
Certainly. And Tanusha has a question. She'll ask it over dinner.